Hello, congratulations on the win of India over England in the Cricket World Cup 2023. Now, today we are going to discuss the last part of our subject, the negative refractive index. Up to now, we have almost finished the theory part except the format principle. We have seen some of the consequences in the last discussion. And today we are starting with the format principle. Then we'll see some applications and some references. There we'll stop. So we'll start with the format principle. In the double negative media or the left-handed media or a media with negative refractive index. Now when we say format principle, it is based on the principle of least action. The ray of light between 2 points, if it travels from a point to another point, then it takes the shortest path. That is what is Fermat's principle. And there were objections that if there is a DNG media or a negative refractive index media, in that media this principle will be violated. Now let us see analytically whether it is being violated. Now what does this say analytically? It says L, which is the optical path, is equal to A to B integration over the points A to B, A and B being the points between which light is propagating, integration over A to B of N dl, N being the refractive index. And the condition is for format principle to hold, delta L is equal to 0. This is the condition. And this is going to be violated if n is negative. If n is positive, this condition holds. If n is negative, this is going to be violated. Now, what does this mean? What does this equation say? It says, if you properly look at its philosophy, it says that the optical length of the actual path chosen by the light is L. This can be negative or this can be 0. Which can be 0 or negative? The optical length, not the physical length. Remember, it is the optical length which can be 0, which can be negative, but not the physical length. So this part people neglect, that this can be optical length can be negative or 0 or null. That is what happens in case of DNG material or negative index material. It is negative or null. Therefore, uh, the format principle is not violated. Now, if that happens, then the path of light is necessarily not uh, shortest in the time. In terms of time, it is not the shortest, which is t is not equal to L by C in that path. When this happens to be true, if it is negative or null, then t is not equal to L by C, L being the optical path. Because L can be 0, if L can be 0, then 0 by C is 0, so t is equal to 0. This does not happen because it takes some time to travel from A to B. So t will not be 0. So necessarily t is not 0. This is this is how Fermat principle is valid. It is not uh, invalid in case of DNG material. Now let us consider it with one example, simple example. So let us consider this slab that we considered earlier. So slab is a DNG slab, double negative material slab or negative refractive index slab. Within the slab, n is negative, n is less than 0. We have a source point. From this source point, the light travels, and within the slab, the light is focused onto the point F1. Then again, it continues to travel from F1, and outside the slab, it is focused at F2. It is a simple slab, rectangular slab. Now, if n is equal to minus 1, suppose n is equal to minus 1, refractive index is equal to minus 1. Why you choose refractive index is equal to minus 1? Because outside the slab, we have free space where refractive index is 1. So therefore, its opposite we take n is equal to minus 1 inside the slab. Now, if n is equal to minus 1, then the optical length is equal to 0. Optical length means the optical length from source to F1, the first focal point within the slab, or source to F2, the second focal point outside the slab. How can optical length be 0? Now you know the optical path length is equal to 2 pi by lambda. Sorry, optical phase is equal to 2 pi by lambda into the path length, physical path length. Now, if physical path length is lambda or any multiple of lambda, then phase is equal to 2 pi, or 2 pi is same as 360 degree, that is equal to 0. So, if the phase is 0 in same phase, then effectively length is practical phase length is optical length is 0, because phase is 0, so 0 is equal to 2 pi by lambda into optical length. 2 pi is not 0, lambda is not 0, so optical length has to be 0. That is why this happens. So for n is equal to minus 1, optical length is equal to 0. Now under this condition, we have two foci, F1 and F2. At these foci, there will be three conditions. And again, under the condition n is equal to minus 1, all rays will be recovered at the foci. So at any point of F1 or F2, all rays are recovered. So the rays which are coming into the slab, they will be recovered at F1. Rays which are coming out of the slab will be recovered at F2. Now, if we consider the foci, any of the foci or both of the foci, in these foci, the phase is fixed. Phase does not change. So phase is the same as the phase at the source. That is point 1 to be noted. Second point is the intensity of light at both these foci will be weak. Why? Because there are two walls, two parallel walls of the slab. At each wall, at the first wall, which is the wall towards the source, the light, some of the light gets reflected. Similarly, at the second wall, which is toward the foci 2, or which is between foci 1 and 2, F1 and F2, some of the light will get reflected. Because of the reflection, the intensity U is weak at these points. Now, suppose n is equal to minus 1 under the condition that epsilon by epsilon 0 is equal to minus 1 and mu by mu 0 is equal to minus 1. They can be different with their product is equal to minus 1, but let us consider this. Epsilon by epsilon 0 is minus 1, mu by mu 0 is equal to -1. If that happens, then the wave impedance of the slab will match with the wave impedance of the surrounding. What is the wave impedance of the surrounding? It is root over of mu by epsilon. Now mu and epsilon both are 1, therefore it is 1. Now what will be the wave impedance of the slab? It will be root over of epsilon r by mu r, which is -1 by -1 root over, that is again 1. So there is wave impedance matching. Because the wave impedance matching is there, so there will be proper transmission or on the incident waves, normal incident waves will pass through the slab to the surrounding. Therefore, the source will be exactly reproduced at the foci. So, on the forward principle is valid even in this case. Next. There is another objection which is about superlensing. People said that there will be superlensing. Now, what is superlensing? Let us try to understand that. Usually, k is the wave vector. So, you are incidenting a wave vector k onto a lens. If you are doing that, the wave vector can be seen as combination of two components. One component is k perpendicular, other component is k parallel. K perpendicular is perpendicular to the surface of the lens, k parallel is parallel to the surface of the lens. So that is how you look at the k vector. So if it is going towards the lens and it has to pass through the lens. Now what happens in this case, generally in the right-handed media, what is going to happen? In the right-handed media, we know omega is equal to c into k, or omega square is equal to c square into k square. Now k has two components, therefore we can write k square is equal to k parallel square plus k perpendicular square. Now let us say that we want maximum of k to be focused through the lens. Then in that case, k parallel has to be greater than omega by c. If k parallel is greater than omega by c, then k parallel square plus k perpendicular square is equal to omega square by c square. K parallel is greater than omega by c. Therefore, k perpendicular has to be imaginary. If k perpendicular has to be imaginary, then in the propagating wave, which is of the form exponential I k r. Now for perpendicular component, it will be exponential I k perpendicular r. Now exponential I k perpendicular r, that we can write k perpendicular is imaginary, so that we can write exponential I into I absolute k perpendicular into r perpendicular. Now I into I absolute k perpendicular is minus minus of absolute k perpendicular, which means exponential, this part becomes exponential minus absolute of k perpendicular r perpendicular. This is an attenuating factor. Next. Since this is an attenuating factor, therefore the wave component corresponding to the perpendicular k perpendicular, those wave components will decay or they are being lost during the focusing through the lens. Those are going to be lost. And if they are lost, under what condition they will be lost? Delta max path difference, maximum path difference will be approximately equal to lambda. So they will be lost in that case. Now we have the lens with negative refractive index. So n is less than 0. If n is less than 0, then phase will change sign. So exponential j k perpendicular r perpendicular will become exponential minus I k perpendicular r perpendicular. So if k perpendicular is imaginary, then that part will become exponential minus I k perpendicular r perpendicular, which will be approximately exponential minus I into absolute k perpendicular r perpendicular. I minus I is 1, so that will be exponential k perpendicular absolute r perpendicular, which is a enhancing factor. Instead of diminishing factor, it becomes an enhancing factor. Therefore, K parallel. This indicates the first thing is K perpendicular indicates K parallel greater than omega by C. So even if K parallel is greater than omega by C, K perpendicular is not lost. Therefore, the wave component associated with K perpendicular are not lost. So when they are focused, the K perpendicular is also focused, K parallel is also focused. So we say that type of focusing to be superlensing in the lens because these are focused. We call this type of lens to be a superlens. So superlensing is possible with DNG material or negative refractive index material. So lens, if a lens is made of negative refractive index material, then superlensing is possible. Now, let us see the simulation of perfect lens phenomenon. So in the simulation of perfect lens phenomenon, we have a source in the right-handed medium. Then we have a slab of left-handed medium. Now, what happens from the source? The light ray comes to the left-handed medium. Then they are focused within the left-hand medium. So the middle green point, that is the focus within the left-handed medium. From there, they come out again at the right-handed medium. You have to note that in the within the left-handed medium, from right-handed medium to left-handed medium, the wave propagation is backward and the deviation is negative. The deviation of ray is negative. Similarly, from LHM to RHM, wave propagation is backward and deviation is and again negative. Or, so therefore, we have got two foci, both these green foci. Its simulation you can see in the electromagnetic simulation. If you do, you see in the bottom we have a source in the right-handed medium. From the right-handed medium, it comes to the left-handed medium. In the left-handed medium, it is becoming focused onto a point. You can see the point where it is being focused then. And in the left-handed medium, you can see the backward propagation of the wave. In the right-handed medium, you can see the forward propagation of the wave. Now, from the focus point in the LHM, it is going forward because S is forward or pointing vector is forward, so energy propagation is forward. That goes to the right-handed medium. You can see in the right-handed medium, again it is becoming focused in the right-handed medium outside the LHM and where it is propagating in the forward direction. Next. Now we will consider an application. With this application, we stop. First see the top left figure. We are incidenting a source onto a metallic plane, ground plane, we call it a ground plane. So a source, from the source electric field is incident onto a metallic plane from where it gets reflected. So note this reflection. So the reflected wave you note. Then on the ground plane we create a bomb, metallic bomb, and other parts remain same. Look at the reflected wave. The reflected wave changes, it divides into many reflected wave as if it is coming from different sources instead of one source. Now in the bottom figure, you see the same thing, but on the bomb, we have put double negative material or negative refractive index material appropriately designed. The design is appropriate. So if you design it appropriately, you can see the reflected wave is similar to the reflected wave from the metallic ground plane, which means if you put such a material, then one cannot find out, looking at the reflected wave, one cannot say that below this material or from the reflected wave, one cannot conclude that there is a bump. So bump is clocked or hidden. Next. This shows the electric field distribution uh, and the design of the clock that is given on that is put on the metallic bump. Next. And this one again shows when we have normal incidence from the top onto the bump, how the wave is getting reflected for the normal incident at 9 gigahertz. Next. This is also showing the same thing. Here you can see when we have the bump, it is not exactly going back, but it is going back in two different directions. Next. Now we have the clock here. Now if you have the clock, you can see it is going back normal, only upward. In the upward direction, it is going back in normal direction. So normal incident, it is going back normal in the normal direction in the upward direction using the clock, which is designed based on the negative refraction principle. Next. And this shows you the reflection from a perfect ground plane on the top left. Then when we have a on the top right is the reflection when we have a metallic bump for the normal incident, and bottom is the reflection when we have the clock designed appropriately using the negative refraction principle. Next. So with that, we come to end of our discussion on the applications. Finally, if you are interested in this topic, here are some books uh, through which you can go through, and one of them is by Professor Anant Ramakrishnan, who is at IIT Kanpur, India, one Indian author. Uh, that book is very good for understanding the physics behind it. And the last book by Elfederias is very good for understanding the engineering part of mathematics. With that, I thank you for staying with patience through this series, and we hope to meet you in another series soon.